Hello everyone, welcome to this webinar. My name is Arvind Krishnan and today we're going to be talking about leveraging 3D printing capabilities for topology optimized design. This is a area that I am extremely passionate about because this was a central theme of my research as well. So I look forward to presenting this to you guys. Before we get started, I would like to add that if you would get a link of this presentation online at our YouTube channel, and if you would like to tweet or give us some feedback, you can always use hashtag GoEngineer and tag at GoEngineer as well. We will have a question and answer session after this webinar is completed. So let's get started. McKinsey did a review of the industry and kind of what to expect in the next 3 years, kind of a thing, and about the 3D printing industry. And what their findings stated is that 40% of the people that they interviewed had not heard much about 3D printers, whereas there was still a substantial amount, 10%, who thought it was highly relevant to them today, whereas another 30 to 40% people thought that it's something that will be useful 3 years from now. This is great to know for someone who is interested in the adoption of 3D printing in everyday processes in different companies. And this is also has a positive great side to it, which is the fact that 3 years ago, a lot of the conversations that we were having is, hey, what is a 3D printer and what does it do, as compared to now, where a lot of the conversations are, hey, how else do we leverage the capabilities of a 3D printer to better streamline our business processes. So having said that, the outline for today is going to be, we'll talk a little bit about 3D printing adoption, and who needs it, why do they need it, what can they do with it. Following that, we'll talk about design for additive manufacturing. This is specifically if you're considering using an additive manufacturing methodology as compared to something else or a traditional method. We will talk about optimization, what it means, and what is topology optimization. And once we define that, we can talk a little bit about constraints for additive manufacturing, which would be different from traditional manufacturing processes. And we can tie all these concepts together using a case study towards the end. So 3D printing adoption. It's important to note that 3D printing lets you make a lot more organic shapes as compared to before, where a lot of the shapes are very non-organic. And hence, because of this, the main industry that has taken to 3D printing is defense and healthcare. Healthcare already had to make a lot of organic shapes, and hence their processes were very expensive, and it became cost comparable to switch to an additive manufacturing process. To go into a little more detail about this, if you look at this train, it represents a very traditional shape made with traditional manufacturing methods. And as the speed of these trains increased, and as it entered a tunnel, it created a loud boom sound just because of the pressure that got accumulated in the front of the train. To solve this problem, one of the engineers looked at the design of a beak of a kingfisher. And the design of this beak of a kingfisher is such that as it enters the surface of water to grab a fish, which is its main source of food, the entrance of the beak to the surface of the water creates a minimal ripple. And the bird is banking on the fact that its reaction time to get to the fish is going to be faster than when that ripple gets to the fish and alerts the fish to run away. So keeping that in mind, the design of this beak is to ensure that there is a minimal pressure accumulation in the front as it enters that surface. Looking at this and inspired by this design, the engineer went ahead and redesigned a lot of the trains where now the speed can be a lot higher just because there's not that much of a pressure accumulation in the front. So the modification in shape leads to a more organic shape, which has better design properties. And this is the central theme of what we're talking about today, where you can make more organic and lighter designs when you manufacture with a 3D printer or an additive manufacturing. And of course, healthcare is one industry that has taken to this, and we're going to look at some examples soon where an already expensive process was replaced. So, just quickly looking at some examples of where this has been used, 3D printing of vital organs has been one very important step, where before surgeons used to look at 2D scans, now you can take 2D scans and make a 3D print out of a vital organ so that surgeons can do pre-surgical planning before they enter the operation theater. Another place is dentures, where expensive casting or molding techniques were replaced with more traditional shapes or more organic shapes that would conform to each person's teeth structure. Okay, and finally we also have implants. And implants, each person's body shape is slightly different, and if you want a good fit for each and every person, here is a hip implant that has been designed for a specific person. Like we said, biomedical parts are tough to manufacture. They have to be organic in shape. You can't replace them, and hence it made sense here. Similarly, taking the same concept to the other industries, we've seen how, because of a lot of manufacturing constraints, a lot of the shapes today are very non-organic. And if you want drastic changes in design, where you want to go away from hoping 5% decrease in mass to 30 to 40% reduction in mass, then this is a process that needs to be taken into account for end-use manufacturing. Another example is the aerospace industry. There's a lot of companies now designing not for maximum costs, but maximum weight. The goal is for a maximum allowable mass, and when mass is such an important criteria, it really does pay to go to an additive manufacturing process. So, having said that, let's talk a little bit about design for additive manufacturing before we go into optimization. So complexity has no additional costs. However complex your part is, if you're manufacturing it through an additive process, the complexity of the part does not take additional material, nor does it take additional time to manufacture. There are of course some things you need to take into consideration, but in the most parts, you are not. There's no problems in terms of how complex the part is, as long as it can be printed. The other, of course, is low material wastage. There is a buy to fly ratio, and in some extreme cases, you could need as much as 10 times the material as compared to the weight of the final part for when you're using traditional manufacturing processes of complex components. And that's where an additive manufacturing process is a lot more beneficial, where it's not only the fact that you are using less material for your designs, you also need less material for the process itself, because the material you waste cutting stuff out is not as much. And finally, support material considerations. This is a new thing in additive manufacturing that would be different from traditional manufacturing processes, because an additive manufacturing process needs support material, which you would not need otherwise, let's say, in a traditional process. So that's one thing that we need to take into account, and we'll talk a little bit more about this soon. So having said all this, let's talk about optimization. And what is optimization? Juke Dubrowski spoke about the fact that the principal objective of engineering is to develop the stiffest structure possible by using the least amount of material. So what does this mean? Obviously, let's say you have two variables, x1 and x2, and your goal is to optimize the mass of your design by changing these two variables. In a very theoretical sense, if you decrease both those variables down all the way to 0, then let's say the mass goes down to 0. However, you have some constraints. You don't want the stress to be above a certain level. You don't want the displacement. You don't want the part to bend too much or deform too much. And hence you get these constraints that prevent the mass from going down to its theoretical minimum. But that's when you get an optimization point which conforms to all the constraints, but still is the least amount of mass possible. So talking about constraints, now we can look at specific constraints for the additive manufacturing process. Now there are different technologies out there, and the different technologies might have slightly different constraints. Okay. But these are some minimal things that you need to take into account when using an additive manufacturing process. For example, the maximum size of the printer bed. This seems like a no-brainer, but given whatever the maximum size is, your part cannot be bigger than that. For example, and this is one of the reasons that more expensive printers have a bigger design, bigger print bed volume as well. You also have a smaller size that can be printed, which is a minimum size allowable. Okay, there is a minimum angle where support is required. Again, different processes have different requirements, but some additive manufacturing processes do not use any support, and they prefer a minimum angle of 45 degrees. There could be some other processes where support material is always used below a part. For example, a polyjet process that Stratasys does. So, these are additional things that need to be taken into account. Clearance between separate regions and minimum contour thickness. I'd like to pull up this picture real quick to talk about that. So if you have two different struts, and this is especially true with an electron beam selective melting process, where there is a minimum gap that's needed between between different separate regions. And also the minimum contour thickness is the minimum thickness that a particular region can have, that needs to be accounted for as well. One thing we haven't spoken about is the layer thickness and things like that, and all those also can be optimized and improved to make sure that you get the best quality of your part. All right, so let's talk about the different types of optimization. Something like SolidWorks simulation can do dimensional optimization, where they look at specific parts and specific dimensions, specific fillet radius, and in this case, a heat sink is optimized by looking at the source of the heat and going from a given initial design to a final design where the maximum temperature should not go more than a certain expected level, but then as long as that holds true, it's going to try to get the least amount of mass possible. Okay, there's also topology optimization. So something like Solid Thinking Inspire does topology optimization, where you have this initial shape. This is an air spring carrier by Lieber Group, and the weight, which was initially at about 8 kilograms, was taken, and using Inspire and using topology optimization, this weight was reduced down to about 4 kilograms. So you can see that a lot of the main regions that this design interfaces with other components are still held. For example, those holes on the left, but the rest of the design is optimized to give a better transition from the region of the load to the region of the restraints, while decreasing the mass as much as possible. The third type of optimization is a lattice-based optimization called variable material density, where the material density is no longer you either have material here or no. Now you can have a lattice structure of various relative density such that your designs are selectively hollow on the inside. What this does is it is very useful in some unique applications like compressive load applications, where for example, a bumper of a car can have a variable lattice structure on the inside such that there's actually place on the inside for it to compress to, and hence it can take a lot more load for a given amount of deformation and creating better impact applications. Thermal insulation is another place where, because of the air filled on the inside, the part overall is going to act as a better insulator. On the subject of variable material density, the picture you're looking at right now is an open cell metal foam. This is made with a different manufacturing process, but it's important to note that an open cell metal foam has pockets of air on the inside, and it's open on all sides. So we were talking about support materials earlier, and if this part was additively manufactured, that would be filled with support material initially, and using maybe a soluble fluid, that support material can be removed out. The reason I bring this up is there's also a closed cell metal foam which you would not be able to manufacture through a 3D printer, because the pockets of air on the inside, which are closed by metals, would be filled with support material, and there would be no way to remove them out because you cannot access those regions. So let's tie all this in with an example. Okay, here is a case study where you have 4 fixtures in the bottom, and there is a weight that's been held with the 4 holes on the top. Once again, solid thinking Inspire was used to do this, where whatever is in red is called the design space, and it can be shaped to, material can be removed from that region. So a topology optimized process is used, and as you can see, a lot of the material has been removed to come up with this shape. Now this is a shape that would be very hard to develop by analytical methods, and hence a numerical simulation method is very useful in this case. After some cleaning up, you can create a new CAD geometry which is a lot more organic in shape as compared to the initial design, but more importantly, it has much smoother transitions than the picture that you see in the middle. And finally, once you make sure that all of these that this shape conforms to the constraints of additive manufacturing, you can go ahead and print it in an additive manufacturing process to get you something that looks like this. So once again, it would result in tremendous weight savings as compared to the initial design, but still adequately perform the functions that the part was designed for. On that note, I'd like to conclude and thank everyone today for attending, and feel free to let me know if you have any questions. Here's a list of references that I had today, and here's my contact details in the bottom if you would like to contact me. Thank you.